Today's problem is median in a row-wise sorted matrix. Difficulty hard, accuracy. Accuracy is pretty high. I'll tell you why that might be in a second. Given a row-wise sorted matrix of size n times m, where the number of rows and columns is always odd. Okay, that's good. Return the median of the matrix. Now, yeah, that would be something good to clarify. Number of rows and columns is always odd. You have to do more work if that's not the case. Odd number times an odd number is an odd number, and so there's always a middle number. Now, if you had, like, we have 3 by 3 matrices here. It doesn't have to be a square matrix, but you could have a 5 by 3 matrix that has 15 elements. If you had a 4 by 3 matrix, now that has 12 elements. Now we're looking for the 6th and 7th element and averaging those, so it's harder. We don't have to do that. Matrix, okay, so they give you the matrix. Sorting the matrix elements gives us this, and so 5 is the median. Now, here's the thing. I tried doing this this way just to see what would happen. I didn't think it would work, but it did work, and that is, yeah, why don't we just do a nested loop through the matrix, put everything in an array, sort it, and take the middle number. Now, usually the obvious or the naive solution like that will time out. In this case, it didn't. It worked fine. So you can submit that, and it works. Same thing here. We're going to do it a different way, but in any case, n, m are each between 1 and 400, so 400, well, I mean, it can't be equal to 400 because it's got to be odd, but 400 times 400, what is that? 160,000? That's not a lot. 160,000. You go through that, sort it. Matrix, the numbers in the matrix will be between 1 and 2,000. Expected complexities. N log m. Yeah, that's right. And for each row, we're going to binary search. Yeah, for each row, there's n rows, and we are going to binary search the contents of the columns. So that's n log m. We're going to do a binary search over the search space for the median, which would be max val minus min val. So that all makes sense. All right, let's take a look here. We have rows, we have columns. We are going to initialize min val to something big, initialize max val to something small. Get the actual min val and max val. Now, you might be tempted to think that the number in the top left, is that right? Yeah, top left is the min, and the bottom right is the max. That's not true, although it is true in these examples, perhaps intentionally, but there is no constraint between one row and the next row. It's just the constraint is just that each row is sorted. So, the second row, for example, may have all the numbers in the second row could be smaller than all the numbers in the first row, or they could all be bigger than all the numbers in the first row. We don't know. That's not given. It's just that each row is sorted. That's all we can count on. So to get the min val, we have to go down the first column on the left and take the min value. For the max value, we have to go down the column on the right and take the max value. That's what this is doing. All right, let me see how much I can get in here. I don't think I can get all of it. We don't need the last line there, return median. We can just kind of remember that. We can't get the required count. Okay, well, let's do this. Let's do the first example. Required count. That's where the median is. So in this case, let's do the first example, rows times columns. 3 times 3, 9, plus 1 is 10, divided by 2 is 5. So with 9 elements, the fifth element is the median. All right, let me get a pen here. Let me just write that down over here. Our required count for this is 5. Okay, now back over here, let me scroll that up a little bit. And that is everything other than return median. So, okay. So let's do this. Actually, did we do that up here a little bit higher? Yes, we got the min val and the max val. The min val for this example is smallest number in the first column, that's 1. Biggest number in the right-hand column, that is 9. Median is 0. All right. So we've got the search range. The median has to be between 1 and 9. We have the required count. We're looking for the fifth element. And now we are going to do a binary search between low and high. We're going to do a binary search on the median, the possible range of the median. Okay. How do we do that? Well, yeah, hang on a second. Okay, well, let's go ahead, one step at a time. Oops, whoa, how did that happen? Can I undo that? Is there an undo here? Let's see. Okay, mid is low plus high minus low divided by 2. So that is 1 plus 8 is 9. 1 plus 8 is 9 divided by 2 is 4. Okay, 4. Count is 0, 4. Okay, so now what we're going to do is we are going to count the number of elements in the array that are less than or equal to 4. Right? If there are not at least 4 elements less than 4, keeping in mind that we're looking for the fifth element, then 4 is too low. If there are at least 4 elements less than 4, then 4 is a possible median. It's possible there could be a smaller median, but 4 would be a possible median. We would continue the binary search, but we would move the high pointer down. All right. Now, here's how we're going to count the elements. I'm not sure how to do this in another language. Actually, let me see if I can scoot this over a little bit so everything is visible there. Whoops. In that case, let me move the frame over. All right. Let's see. What we're going to do is a binary search on each row. Now, each row is an array. Java has a static binary search method on the arrays class. Here's the way it works. You give it an array, you give it a target. If it finds the target, it returns the index. If it doesn't find the target, it returns a negative number. And that number is the insertion point where the target would be if it were in the row. And then you negate that and subtract 1. Why do you do that? I mean, you could just negate it. It makes sense to return a negative number to indicate a miss. So I'm thinking it's to handle the case where the insertion point would be index 0, because negative 0 is just 0, but negative 0 minus 1 is negative 1. So, well, we'll go through and see how it works. Mid. Okay, mid. So we're going to binary search the first row for mid, which is 4. 4 doesn't exist in the first row. 4 doesn't exist in the first row, but if it did exist, the insertion point would be index 2. All right, so what would be returned is negative 2 minus 1, or negative 3. So the index would be negative 3. We're going to do a conversion on that, and we're going to do negative 3 plus 1 is negative 2, and then we're going to negate that and get 2. That is actually the count of of how many elements in the first row are less than 4, which would be the 1 and the 3. Okay? And then count plus equals index. So count, which is currently 0, is now going to go to 2. All right? We're going to go to the next row. Does 4 appear in that row? It doesn't. If it did, the insertion point would be index 1. So what we're going to get back is negative 1 minus 1 is negative 2. Is it less than 0? Yes. So negative 2 plus 1 is negative 1. Flip it, and we have a 1 here. Okay, drop through the rest of it and add index to count. So that is 3. We're going to find the same thing happens in the next row, and we're going to add another 1 to that. And so there's 4 elements in that array, 1, 2, and 2 3s, that are less than or equal to 4. Okay? Now we drop down here. Count. Is it less than required count? Required count is 5, and it is less than required count. That means 4 is too low to be the median. So low equals mid plus 1. Now mid is 5. Low is 1. 1 plus 4 equals 5. Low is mid plus 1. All right? Now we'll go back up to the top of the while loop. Is low less than or equal to high? Yes. Mid is low plus high minus low is 4. 5 plus 4 is 9 divided by, wait, sorry. 9 minus 5 is 4 divided by 2 is 2, and then added to low. So mid becomes 7. Mid is 7. Count, I'm going to just erase the count. Count is 0 at this point. All right, we're going to do the binary search in the rows again. Actually, I'm not even sure how to handle this. But let's do this. Actually, let's erase the index as well here. All right, searching the first row for a 7. It's not there, and if it were there, the insertion point actually would be index 3, meaning that index would return negative 4. So negative 4, and we're going to convert that. Negative 4 plus 1, negative 3. Negate that. Index is going to be 3. Okay, it's 3. Count plus equal index, 3. Good. That means there's 3 numbers in the first row that are less than or equal to 7. Let's go to the second row. The insertion point for 7 in the second row would be index 2. So what is going to be returned is negative 2 minus 1, negative 3. So we come down here, negative 3 plus 1, negative 2. So that is going to be a 2. Add it, we have 5. The same thing is going to happen in the next row. We're also going to add 5. We're going to come down here and say, is count, because there's a lot of numbers in there that are less than or equal to 7. Is count less than required count? No, no, it isn't. Otherwise, median equals mid. I mean, 7 is a possible median, although we're going to continue looking. And high is mid minus 1. So high is 7 minus 1. So this is going to go to 6. Okay. All right. Going through the loop again. Low is less than or equal to high? Yes. Mid equals high minus low. 6 minus 5. 6 minus 5 is 1 divided by 2, which is 0. Low plus 0. 5 plus 0 is 5. Okay, let's just erase that and put a 5. All right, let's erase that and put a 5. Let's erase this, this, and this. All right. Binary searching the rows. There is a 5 in the first row, and it is at index 2. So we want to handle duplicates, although in this case there isn't a duplicate. But index is 2, while 2 is less than 3, and matrix at 0, 2 equals the mid, which it does, increment the index. Okay, so the index becomes 3. That's actually too high, so there can't be a duplicate there. So we'll just do count plus equals index. Count plus equals index, which is 3. Actually, I didn't explain that very well. Index is going to come back at 2. So while 2 is less than 3 and they're equal, increment the index. So the index here does go to 3. Now we say while 3 is less than 3, but it isn't. Now index is still 3, so we add the 3 to the count. All right, next row. There is no 5 in that row. The insertion point would be at index 1, so we're going to get a return of negative 2. We're going to get negative 2, reverse it, that'll be 1, and count, we're going to add 1. There's one number in the second row that is less than or equal to 5, and looking at the third row, we're also going to have one number that is less than or equal to 5. All right, drop out. Is count less than required count? No. In that case, median equals mid, right? Mid at this point is 5. And we're going to do high equals mid minus 1. So high is mid minus 1, which is 4. High is now lower than low. And so that is going to terminate this a binary search. And what we're going to return is this, median is 5. So again, to kind of recap that, what we do is find the search range, which is the maximum element minus the minimum element. Calculate the required count, meaning what is the index, well, what is the count of the middle element. So we have 9 elements, it would be 5. And then perform a binary search from low to high. Calculate the mid and then count the number of elements. And in Java, at least, you can use a binary search for this to count the number of elements in the matrix that are less than or equal to mid. Now, if the count is less than the required count, then the median that we're trying is too low. So we have to change low to mid plus 1. If the count is greater than or equal to the required count, then mid could be the median, or the median is smaller. So we'll update high equals mid minus 1 and continue searching. You know, as in this example, we got, well, 7 is a possible median. There are certainly enough elements in the matrix less than 7, but we keep going and we get the median is 5. Okay, let's get rid of all of these. Let's run a quick sanity check here. All right, yeah, that worked. And then submit. Now you're going to see that I already submitted this once. The first submission was just the simple submission that I said, just take all the numbers out, put them in an array, sort it, and take the middle element. That works. And that is never a bad idea in with an interview question, is to just do some brute force method, and to do some brute force method that will work. Okay, and then if they ask you to optimize it, you can optimize it. But the first of these 2 attempts was just to sort all the elements and take the one in the middle. So anyway, that is it. Please like the video, and you can subscribe for free to the channel. I'll send you problems of the day every day in your inbox, and we'll see you next time.